That's the website for those of you who don't remember. I haven't posted last class's lecture, but I will today. Okay. All right. So almost all devices that we're interested in talking about in this class can be thought of as a heat engine. A heat engine is something that does work, and the source of the energy that contributes to the work is heat. It can be from light, whatever, but it's usually particularly heat. It can be electricity into heat. So in other words, the heat engine essentially converts light or fuel to heat, which is then converted to motion or electricity. In a very, very cartoon perspective, you have some heat input. Let's say you have an enclosed container, just water. Once the water becomes steam, pressure increases, so it expands, it pushes this piston, and then you can have motion, for instance. Very simple, right? Of course, the source of the heat can be solar thermal. You can have concentrated, you build optics to collect light and heat up something. Or it can be fuel. Or it can be electricity, right? You can have a motor directly running it. Okay, we'll talk about a few of those. The key concepts are the heat difference is used to generate the energy, so you need to have some temperature difference between two reservoirs, and we'll talk briefly about that. And of course, examples are all the traditional energy generating systems, such as coal plants, nuclear power plants. Now, nuclear power plants, of course, the heat comes from a nuclear fission reaction, right? We break some atoms and then create a lot of energy, and it heats up water. It works exactly pretty much the same way. It runs a turbine, generates electricity. Solar thermal plants, we'll show a few examples, work pretty much the same way. You typically heat up molten salt, or it can be water, but typically it's molten salt or some special kinds of oil. Primarily because those materials retain heat much better than just water. Geothermal, exactly the same way. You get heat from the ground, heat up, and then you can have different mechanisms that bring the heat up. Thermoelectric devices, we very briefly talked about it in one of the first lectures. Essentially, that generates heat from electricity. Clearly, it's a very inefficient process, so it's just mentioned there. Not so important. The most common heat engine, which you've all seen, is this, the internal combustion engine, and essentially it works the same way. And I won't go into much detail, but you essentially have a cylinder, a chamber, whose intake and outtake can be controlled, typically with a computer nowadays, and the piston is attached to some crankshaft. So in this case, you have an intake, air-fuel mixture is drawn in, so it's rotating this way. So you pull in the fuel, then the valves get closed, and because this comes back, it compresses the fuel air mixture, which essentially also increases it decreases the ignition point essentially. And then you have a spark plug, which ignites an explosion. And because of the energy released as the gases expand, because they heat up, and that pushes the piston down. Okay. And as it comes back out, as it turns back out, you have exhaust. It pushes the burn gas out. Very simple. So it's the simplest form of, most common, not necessarily the simplest, most common form of heat engine. Okay. Now, you can divide heat engines in a couple of different ways. You can have either a direct conversion system, or you can have an indirect conversion system, and we'll talk about that in a second. Direct conversion systems are essentially light going to electricity. In this case, we're generating electricity. Or you can go from light to fuel, and then fuel to motion, or electricity. Electricity, I was referring to a turbine or a motor, right? Either you're generating energy or you're using the energy to do some work. And the direct systems are what the most familiar ones are photovoltaics. Of course, photosynthesis. In that case, you're converting sunlight to fuel, food. Of course, all the other things like we talked about last time, hydro, tidal, wind, all that. It's illustrative to know the conversion efficiencies of all these processes. These are typical numbers. And this will become more important and relevant later in the class when we actually talk about, for instance, photovoltaics and energy, other solar thermal, for instance. How do they compare to some of these processes? And efficiencies become quite important. Electric generators are pretty efficient. You can get high these basically turbines turn mechanical to electrical, produces electrical currents. Mechanical to electrical energy conversion can be pretty efficient, over 80%. Motors, of course, convert current to motion, the opposite of a generator, right? Again, the efficiency can be quite high. Light to heat, of course, can be very high. That's how you either going through fuels or directly. We had 90% or so. And chemical to heat primarily refers to fuels, right? Combustion and things like that. Again, can be quite efficient. When we come to photovoltaics, you will see those efficiencies are very, very high compared to what can actually be done from light to electricity, for instance. Okay. The key limiting efficiencies, and we'll look at this a bit more detail. Heat to mechanical is the Carnot cycle, which we'll talk about next, which is basically heat engines and all solar thermal applications like solar cookers, all that stuff. Not photovoltaics, but all the heat engine-based systems. Photovoltaics is a little bit different. We'll talk about that later in the class, which is the next part, light to electrical energy. And that is primarily also determined by thermodynamics, but you have to treat that slightly differently because you have to deal with the quantum mechanics, because you have some limitations with the band structure and how the charge carriers respond to light. Light to fuel, of course, is photosynthesis, and that's what happens naturally. So, in all the cases, thermodynamics places the upper limit. So we need to kind of understand some very, very basic things. And I won't, again, go into huge detail, but we need to know a few things. You have seen most of this before, but make sure you review them. It's good to understand where the energy conversion comes from before we actually start designing systems to do the energy conversion, or what limits the energy conversion phenomena. The first law of thermodynamics is essentially energy conservation. It's fairly straightforward. Delta U equals Q minus W. Delta U, so we're talking about a closed system now, okay, one system. So delta U refers to change in the internal energy of the system. So that could mean many things. You can have changes of state, water becoming ice, water becoming water vapor. So you can have all kinds of things going on there. Q is the heat added, obviously whatever comes in. W is the work done. So the heat added minus the work done is, of course, a change in the energy of the system. It's common sense, but clearly for a solar cooker, we already kind of addressed that to some extent, right? Remember? Q is essentially whatever heat is incoming into the solar cooker. W is whatever gets absorbed by the food, essentially for cooking. And the difference is the temperature. Of course, we also have to, the W must also include the heat losses that go out of the system as well. And then we can calculate how much of fuel can be generated or what work can be done. The second law of thermodynamics essentially talks about entropy. Less important right now, but it's important to understand that the entropy delta S is always positive, which means that it's always either increasing or remains the same. This is a little abstract, and we'll come to it when it becomes relevant, but these are two things you should be aware of. Okay. So again, like I said, I'll post a few resources online so you can take a look at some of the basic ideas. But these things we should keep in mind. Now let's look a little more detail at heat cycles and heat engines, because these are what determine efficiencies in all thermal processes, not photovoltaics. Okay? Heat engine essentially can be thought of as a machine that's able to do work based on the temperature difference between two reservoirs. So that's the most general way to think about it. So you have a source of heat, which of course in our case is the sun, or if it's collected onto something else. And you have a sink of heat. So the source of heat is a TH, sink of heat is a TC. TH is hotter, so higher temperature than TC. T of course refers to temperature in this case. So Q in is the heat input into the system, so that's the heat engine. Q out is the heat out of the system, and W is the work done by the system. Of course, the first law of thermodynamics tells us that W should be equal to Q in minus Q out. Right? So the Carnot, so there are many different kinds of heat engines, and we won't go into any much detail there. But the two main ones are the Carnot engines and the Stirling engine. And the Carnot, and there are very fundamental differences between them. But from our perspective, what you need to know. For solar thermal and in general, thermal applications, the engine performances are defined based on what I call pressure volume curves, because as you remember, there are fluids that change their pressure, change their volume, right? They expand, run something, and so on and so forth. So that's what those are drawn on typically. So you have a situation where your volume decreases, pressure increases, so it's compression. And then you have expansion, volume increases, pressure decreases. Okay, and then the same thing happens. So that's a cycle. It's a reversible cycle. Okay, it's an important criteria for Carnot engine. Okay, the Carnot efficiency is a theoretical efficiency that is attainable. So we'll talk about that briefly, but highest possible efficiency that is attainable. And we'll relate this to photovoltaics later on. So keep this in mind. Obviously, this is for a heat engine. And that's basically the temperature difference between the two reservoirs divided by the hot temperature times 100%. That's approximate. That's the theoretical limit. Now, during the expansion, you get the heat coming in. So you can think about the fluid expanding. And as it compresses, you'll see the heat coming out. And the difference between those two is the area within this curve is the work done by the engine. And that work done by the engine is determined, there's an upper limit to that, determined by this Carnot efficiency. Okay, and that's how that's calculated. Okay, the Stirling, again, you don't need to know the details, but the Stirling engine, Stirling cycle looks a little bit different because you get these very constant volume changes in pressure. So the only difference between that and that is that you can get these constant changes. And in theory, you can have Stirling cycles that can reach the Carnot efficiencies, but in practice, typically they don't. Obviously, all of these are theoretical, right? In a real engine, you never get to these kinds of efficiencies. It's useful to understand where the limits come from. Now, the Carnot theorem is basically what determines upper limits for efficiency. It says that there are two things that come out of the Carnot theorem. One is that reversible heat engines, where you can retrace the states, like those are closed curves, are more efficient than irreversible state engines. Obviously, in practice, nothing is reversible perfectly because you'll always get losses from the system. So obviously, it's theoretical. So it says that all irreversible heat engines between two heat reservoirs are less efficient than a Carnot engine operating between the same reservoirs. Okay. It also implies that all reversible heat engines between two heat reservoirs are equally efficient with the Carnot engine operating between reservoirs, theoretically, including the Stirling engine. Okay. But in practice, you can have, of course, very different performances here. Now, a solar thermal plant, as we'll show in a minute, is typically a Stirling engine. That just has to do with the design. Okay? And all of this essentially comes from the second law of thermodynamics, which is the entropy. Again, I won't go into the details of that, but I'll post some sources that you guys can take a look at. Now, what does that mean? If you want to look at this a bit more quantitatively, the Carnot efficiency. So actually, I'm going to start. Let me see. Okay, I'm going to start here. So in this case, the efficiency of let's call it a solar thermal system, would be two things. One, you have an optical efficiency, which is error collection, which is the efficiency with which you're collecting the light from the sun and sending it to something. Okay, I'm making it very general. Obviously, if you have a solar cooker, it's into the cooker, right? Within the confines of the cooker, and so on and so forth. Multiplied by the heat engine, which actually does the work. So you have a collector and you have something that does the work. They're two different things, subsystems, right? So that's why you have an efficiency term in the collection multiplied by the Carnot efficiency. This is theoretical, so you have the upper limits here. And the Carnot efficiency, as we saw before, is 1 minus Tc over Th. Collector efficiency, now we'll go into a little more detail, is defined as the absorbed heat by the collector, which, if you remember in the solar cooker's case, again, I'm just drawing an analogy, was just whatever heats up, right? Which in that case was the bottom black plate or something, right? Or the cooker itself, right? It's whatever heats up minus the heat loss divided by whatever is coming in. Obvious, right? Now, the heat loss, if you only include radiative losses, remember we have convection and conduction, but I'm ignoring them for the sake of simplicity. If you only include radiative losses, then you can use Stefan-Boltzmann Law, which we saw it last time, right? Remember what does the Stefan-Boltzmann Law say? It says the flux, power density, integrated over the entire spectrum of interest of a radiating black body is given by sigma T raised to 4, right? That's the hot reservoir. That's the heat loss, right? Now, epsilon is essentially what's called an emissivity, which is a measure of how different from a ideal black body is the actual reservoir. Okay, it's again, I'm not going to go into much detail, but if epsilon is 1, which means it's an ideal black body. If it's less, and it's always less than 1, it means it's a little bit poorer absorber as well as an emitter than an ideal black body. That's all that means. It's a constant called an emissivity. Okay? And A is the area, so it's a surface area. Because remember, the power density was always in units of area, right? So you multiply the area to get the total heat loss, and the heat loss. And it's greater than or equal to because you have some losses in addition to that from conduction and convection, which we have in the Carnot before. And the incident light, of course, is the incident solar intensity or irradiance, our power density, integrated over the entire band, right? Which is, of course, sigma T raised to 4 for the sun, as the T is the surface of the sun, 6,000 Kelvin or so. Times C. Now, C is something we'll see later on. It is the concentration factor, which essentially means if you're collecting light from a large area and sending it to a smaller collector, then you have a geometric factor where you collect it from a large area and send to a small area. So it's a geometric enhancement factor. We'll come back to that, so just keep in mind. And of course, area is the same area as well. This is the area of the collector. Okay? In this case, the collector is the heat reservoir, right? It's the hot part of the heat engine. The TH is the collector. Now, in a solar cooker, can someone tell me what the sink is? What is the other part of the heat engine? Actually, why don't you discuss? Think about it. Think about the analogy of the solar cooker. In the solar cooker, I told you the collector, which is the black part, or the cooking vessel, or whatever, is the hot. And what's the recipient? So why don't you take a few seconds?
Yeah.
What do you think, Jake?
The food?
Yeah, exactly. So of course, so that TC would be the temperature of whatever is getting cooked, essentially, and it'll reach at equilibrium where you have this efficiency. Of course, it can be other things too, but in the case of solar. Yeah. So here we are ignoring the other side, right? So the collector efficiency, clearly, if you take these two equations, plug that in there, you get that. So you can think about it almost like the Carnot, but it's obviously not the Carnot. So it's about 1 minus epsilon sigma t raised to 4 divided by c times isol. Now you put them both together, you get the total efficiency, which is shown right there. And these plots essentially give an example of what that means. Okay? So this is the hot source temperature, so this is whatever the collector is, right? You're heating it up with the sun, let's say. It doesn't need to be, but let's assume. And this is the efficiency with which the total system is working, heat engine and the collector, right? So you can see as this C refers to concentration. So higher the concentration, clearly you're getting more of sunlight concentrated into a smaller area. Your power density goes up, the temperature goes up. Right? Your TH goes up, which means that you will get higher efficiency. So the curves in the red curve, if you look at the same temperature of the heat source, the red curves will obviously have a higher efficiency than, let's say, the brown curve. So the concentration is 10 and 5,000. And we'll see this later on when we'll actually look at concentrators, optical concentrators. That you should be aware of it. Clearly, as you increase the temperature also, the efficiency increases, but beyond something, it starts falling down. Right? Why? Because the loss is also sensitive to temperature, right? So again, this is an important condition, right? Because one would imagine you can just keep increasing temperature of the hot source, right? If the heat engine was the only thing we're concerned about, clearly to increase the efficiency, all we need to do is increase that, right? If you make that infinite, this efficiency goes to 100%, right? But obviously that's not the only thing of interest. We also have this thing to worry about, because we're collecting the light. So that's why you have an optimum situation. So again, these things are important when you start thinking about designing full systems, because you need to look at the whole thing. Again, I don't mean to go into, this is not a class in thermodynamics, I don't mean for you to understand every single detail, but I need you to understand once we dive into the optics where it fits in. Especially when you do your projects, you need to kind of keep that in mind. Okay? Okay, and I think we're almost done with this, but I just wanted to put up a couple of examples of solar thermal plants. This is actually the largest solar thermal plant is actually in California. There's one bigger one which is being built, one in Mexico and one actually in Spain. Those are not quite built yet. The one in California follows this design based on a dish antenna, essentially. It's from San Diego National Labs. It runs a Stirling engine. In this case, the maximum efficiency is about 30%. Of course, this is not the heat engine efficiency, right, which can be much, much higher. This is referring to both the heat engine and the collector efficiencies. And that's pretty high in general for these things. The bigger the system, typically, they tend to be more efficient. In this case, the concentration factor is a factor of 2,000. By that, what I mean is, you see, this is a parabolic reflector, which means it's reflecting light from a fairly big area here, and it's getting focused to some tiny focus right there. And the difference in area between that large dish and the small absorber, let's call it, is about a factor of 2,000 area. That's what that C means. Okay, and we'll come back to this. The operating temperature is about 700 degrees, and this is a little old. These have actually been built. Okay, you can actually see it if you guys drive from, I think it's like outside Las Vegas. If you drive from Las Vegas to California, you can actually see this. There's a slightly different design, and this is actually quite interesting because it's a very different optical design. If you have time, we'll talk about this. But you see, in this case, in this case, you have a set of essentially parabola, right, paraboloids, and you have lots of them, and each of them have their focus, and each of them has something which absorbs the heat, and you can have either multiple heat engines or a single heat engine or something which connects them all. Okay, that's one way to do it. Another way to do it is with that. Okay, what that is essentially is what's called a heliostat. don't know if you can see. If I zoom in, you see what's happening is that you have a big tower. That's maybe 100 meters. So it's a pretty tall. It can be anything, but typically very tall. And you have a focus at the top where typically there are tubes that run molten salt because it gets really, really hot. And you have an array of mirrors on the ground. It's huge, kilometers. And each of them are slightly tilted such that they reflect the light onto the same spot. Even as the sun moves, they tilt and adjust for the location of the sun, so it's always pointed to the same spot. Okay, now you can see the concentration factor in this case can be huge, right? Tens of thousands. So, and it's a different way to do it. It's a much different scale. And this is actually, this is actually an existing system in Spain where you have lots of light. It's called a power tower, and in this case it's running a steam turbine. Okay. So those are the two different examples, and that basically ends our discussion of thermodynamics. So I'm going to stop here for a few minutes if you have any questions. Okay? And let me bring up the... And before I start this... So, are there any questions before I go on? Okay. So what I want, I'm jumping up ahead a little bit on our schedule because we were going to start geometrical optics next week, but I figured much of the thermodynamics, rather than me going through it, you should read yourself. So, like I said, I'll post some links on the website. Take a look at them. Try to, and again, as you go do your research with your projects, you'll see much more appropriate resources. So make sure you kind of dig into it a little bit. Okay. Excuse me. So the next few weeks, what I want to do is focus on the optical engineering part of it, starting from very basic stuff. Geometrical optics, and we'll talk about imaging systems, okay? Because those are things that you are familiar with, you've seen before. And from then, we will start looking at non-imaging systems. For that, we need to look a little bit into the mathematics, Hamiltonian optics, and so on. Okay? So that's sort of the plan, at least for the next couple of weeks. Okay, so jumping into this, the modern view of light, of course, we saw this last week, was that light can be a particle or it can also be a wave. And there are a few fundamental constants that we should be aware of. Photon is the elementary particle of light of the electromagnetic field. It has a mass 0 speed, fixed speed in vacuum of 3 times 10 to the 8 meter per second. And the speed is related to wavelength and frequency by that equation, C equals lambda times nu. And that's referred to as a dispersion relation. So in some materials, so actually, let me ask a very fundamental question. Is the speed of light faster or slower in glass than in air? Slow. Right. So the speed of light is slower. So what happens to this side? Frequency and wavelength. So this equation still holds, right? So let's say speed of light has changed. On this side, what has changed? Wavelength, frequency, or both? I actually discussed. That's actually a very fundamental issue. 10 seconds.
I think only wavelength is changed.
Right. Why? Do you have an intuitive explanation why?
Because the frequency is determined by energy.
Exactly. Yes. Yeah. Very good. Yeah. So frequency, of course, remember, energy of the photon is h times nu. H is a constant, right? If the photon goes from air into glass, its energy shouldn't have changed. It's the same photon. Right? So the frequency has to be constant. Okay? Wavelength changes. It's a very fundamental thing. And most people, we don't appreciate it that much. Not so important for our class. Because the reason being that we will deal mostly with geometrical optics, not physical optics, where this sort of wavelength becomes much more important. In any case, so the basic equations are essentially the energy is h nu, momentum is h over lambda. So those are the few things. Of course, momentum changes in different media, right? Because lambda changes, which is okay. We will come back to that actually when we talk about refraction. Okay, you'll see, right? Like bends. Okay, Planck's constant is that. You've seen that before. Wavelength is in meters. Spatial period of the light waves. Frequency is 1/seconds. Is the temporal oscillation, right? Remember, light waves are electromagnetic fields that change with time. Electric and magnetic fields are a couple, but they change with time, and the rate at which they change with time is frequency. Right? We saw that before. The concept of a ray. Now, you can think of this is a ray of light is actually quite important because we'll talk about ray tracing. In fact, almost all of non-imaging optics and optical engineering is based on ray tracing. So we need to understand what a ray means. Right? Light wave can be drawn as follows. Right? You have your wave. Let's say it's propagating in that direction. This is the wavelength. Distance from one node to the other node, or one peak to the other peak. It's periodic. So this is a snapshot, okay, in time, right? T equals 0. We take a picture of the light wave. That's what it looks like. The wavefront is another important concept. It determines planes of constant phase. Remember, a wave has an amplitude and a phase, right? The phase represents whether it's a peak, whether it's a node, whether it's up here, whether it's a 0, whether it's negative, right? That phase represents where it is on the surface of the wave, let's say, or what location it is. If you look at a surface of constant phase, so in this case I've drawn the phase where phase is 0, let's say, the amplitude is 0. Okay. The distance between these surfaces of constant phase is, of course, the wavelength. And the planes of, if it's a plane wave, let's say, planes of constant phase is called a wavefront. Of course, they don't need to be plane. You can have a spherical wave, so you can have a spherical wavefront. It'll become more obvious when we again look at some examples, but keep those terminology in mind. Okay. Now, if you take another snapshot at a slightly later time, let's say delta t, of course, it's a traveling wave. We're talking about electromagnetic waves. It has moved over a little bit, right? Traveled. How much has it traveled? What's the distance it has traveled? What was it?
C delta t.
Yeah, exactly. The velocity is fixed, right? So it has moved over by c times delta t, but everything else is the same, assuming it's a regular medium. There's nothing funny going on. The ray essentially. So what has happened is that the wave is carrying energy with it. Right? There's a propagation of energy. Why? Because if you look at, if you stay at that, this is space, right? This, by the way, this coordinate is space. If you stay in that position of space, 1 second before, or at 0, I have, let's say, 0 energy here. But if at the same location here, I have quite a bit of energy, right? So energy has been transferred from behind me, in a sense. And that direction of propagation determines the direction of the ray. Okay? And that becomes important actually later on. So it should be clear. Another important criteria for the definition of the ray is that the ray is always orthogonal to the wavefronts. So you can see in this example I have plane wavefronts. The ray is perpendicular to the wavefronts. If I have spherical wavefronts, at the location I'm looking at, the ray must be perpendicular to the wavefronts. So if I change the location on the sphere, the direction of the rays change. Okay, keep that picture in mind. Oh, we'll see it again. Okay, and this is very fundamental. In homogeneous media. Homogeneous media means your properties of the medium don't change with space. Okay, like air, vacuum, or uniform glass. So light propagates in rectilinear paths, which means straight lines, right? You don't bend or anything like that. Now, what happens to light and matter? We saw this just now. So just to reiterate, if you're in vacuum, you have a certain velocity. If you are in some matter like glass, the velocity gets reduced by a factor n, and that n is what we know as the index of refraction of the material. Right? Water, glass is about 1.5. So light can travel about 1.5 times slow. Right? In matter, you also have something else happening. You get absorption. Right? We saw this in the solar spectrum. Remember, AM0 spectrum was nice and smooth, whereas AM1.5 had these huge dips. And those dips we talked about had to do with absorption of light by ozone, oxygen. Sorry, not oxygen, ozone, carbon dioxide, and water. Right? That's absorption. So vacuum it's 0. In a real medium, it's denoted by alpha. It's referred to as the unit absorptions or absorptivity, which is essentially defined by this equation. The energy transmitted through a length L of the medium is e raised to minus 2 alpha L. Now, does anyone know where the 2 comes from? We haven't covered it, but if you remember, it's okay. If you don't, we'll talk about that later. But alpha typically refers to the field, the amplitude of the wave. Okay, it's how much the amplitude of the wave has changed. But energy is what I'm talking about here, is square of the amplitude. Okay, so when you square, so draw the marker so you can see that. No, but the amplitude, if it propagates through a distance z of the material, is given by right? That's the absorption per unit length, right? That's how the amplitude of the wave changes. The energy is proportional to the square of the amplitude. So obviously, if you plug that in, you get the 2. It's obvious, right? We'll come back to that. That's also quite important later on. Okay, so, so another interesting thing to remember, a glass fiber, talking about absorption, has a very, very low absorption. So it's 0.028 per kilometer. That's why we can have internet and so on. To 5%. Okay. Reflection. So the 3 basic things that can happen as light propagates through a medium. You can have absorption, reflection, or refraction. And a few other things, but the 3 main things. Absorption we just talked about. Reflection is what happens when you have 2 different medium, right? The light going from, let's say, it hits air to water, let's say, right? Some of the light gets reflected, some of the light gets refracted. And the only thing about reflection that we've seen before, of course, is that the angle of incidence is equal to the angle of reflection. Okay? The other important condition, which actually will become important in the design of optical concentrators, is the fact that the normal to the surface at the point of incidence, the incident ray and the reflected ray all lie in one plane. Okay? That will become important later on. So what that means is that if you have a curved mirror, That's one way to, if you have light coming in at some strange angle, we know the normal. That is how you determine what the reflected ray, where the reflected ray is going. Okay. The refraction is of course pretty straightforward, determined by Snell's law. So let's say you have two media, index n1, index n2, and the relation incident angle is theta I, refracted angle is theta t. Then Snell's law states that n1 sine theta I equals n2 sine theta t. So if you have a denser medium, if light goes from a lighter medium to a denser medium, it will bend towards the normal, right? Like air to water. So on, so. Again, the incident refracted rays and the normal lie in one plane. So all of these rays need to lie in the same plane. So if you have complex shapes to your interface between the two media, the fact that these rays lie on a single plane become quite important to do ray tracing. Okay. By the way, you can see what has happened here, like I asked before. The photon came in and it's refracted. Energy hasn't changed, but momentum has changed, right? Momentum is determined by the speed, right? The kinetic energy. So here it has slowed down, so the momentum has changed, which is why it bends. It's another, from a wave point of view, that's the reason it bends. Okay. I mean, you probably have seen that in basic electromagnetics. We can also have a situation where you have total internal reflection where no light actually refracts into the second medium. So all the light that comes in gets reflected off. And that happens when the index n1 is larger than n2. So you're going from a denser medium into a lighter medium. And the obvious example is if you're swimming underwater, you can see at some point that you'll see outside if you look at a high enough angle. Right? The water looks like a mirror, essentially. So essentially what that means, that happens when n1 is greater than n2, and it happens when theta, so theta I equals theta c, which is called the critical angle, is sine inverse n2 over n1. Okay? When the incident angle is larger than this critical angle, your light will be completely reflected. So this is actually very useful. Why? Because this is a way to get 100% of the energy reflected. Because if you look here, you can see if you are interested in sending light here, using a simple mirror like this is not necessarily the best way to do it, right? Because you always have some energy which goes this way. If you want to get 100%, you want to be assured that you will get 100% of the energy reflected in a particular direction. You'll be more successful by using total internal reflection. Yep, Faisal.
So does all electromagnetic waves behave this way? Does it, or does it stop behaving like this after a certain frequency?
No, all of them should behave this way. The only issue we haven't talked about, well, there are a couple of exceptions, but is losses in the material. Okay, so you can have this n2 can become, or n1 for that matter, can become complex. And the imaginary part of the index, and we won't talk about this in this class, is basically represents the loss, the absorption loss, essentially. But other than that, yes, any medium. Okay. The other thing, by the way, to keep in mind is that n1 and n2, of course, are not constants. Right? They change with wavelength. So in other words, the refractive index for some material like glass at the UV is different than what it is in the infrared. So if you're trying to design something for solar, you have to keep that in mind, right? If you are relying on this, for that matter. I mean. So you have some spectral dependence of properties as well. Okay. Here we're talking about a single wavelength, right? Okay, you have just this is for completeness. You probably have seen this before. This is another phenomenon for frustrated. It should be another total internal reflection or FTIR. The idea here is that when you have total internal reflection, you can, if you, let's say you have two medium, So in this case, you have two interfaces. So let's just look at the example. You have medium 1, N1, higher index, let's say that's glass. You have medium 2, N2, let's say that's air, lower index. Then you have medium 3, N3, which is a higher index. Let's say it's glass. So basically two slabs of glass very, very close to each other. Okay? And you come in at an angle that is larger than the critical angle. Of course, most of the light, if you don't have this, of course, all the light goes that way, right? 100%, that's total internal reflection, as long as it's larger than the critical angle. But it turns out if you bring this very, 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 very close, within a few wavelengths, you can have some of the light actually leak out, as if it just transmits. You can have a shift, but that's less important for now. Okay? And this is an idea which actually can only really be explained with quantum mechanics, so we won't go into much detail, but essentially light tunnels from the first medium to the third medium. This is actually very useful for some devices, like fingerprint machines and things like that. It's actually used in few devices. Okay? We won't talk much about it, but you should be aware that something like this exists. Okay. So what is geometrical optics? This is what we will focus on for most of the class. It's where we assume that the wavelength is negligible compared to the optics that we're designing, which is typically most of the case. Wavelength of light is really small, right? It's a few hundred nanometers. We ignore everything such as interference, diffraction, all those things, which we won't talk about in this class, but you should be aware these things exist. Hopefully, lots of simple analysis, although we will go into some complex situations later on. The other opposing subject of geometrical optics is what's referred to as physical optics, where you do take the wavelength of light into account. Okay, just again be aware of it. In that case, lambda is non-negligible and so on. Okay, so the basic principle in geometrical optics is based on Huygens Principle. Okay, you've seen this before. Huygens Principle is easiest to understand with an example. Okay, so let's take the case of a point source, a perfect atom. Let's say it's emitting light. Okay, it's infinitesimally small, much smaller than the wavelength. Right? So you have light going out in a spherical wavefront. It's going in all directions. But if I take a snapshot at some instant of time, you have a wavefront which looks like that. You have lots of wavefronts. I just picked one. Right? Okay, let's call that the primary wavefront. What Huygens Principle says is that every point on this primary wavefront now acts as a secondary source point, which means every point on this wavefront now acts just like that and emits its own waves. Okay, so each point there will emit another sphere and so on and so forth. Of course, this is an abstraction. So this is a mathematical explanation. This is not reality, right? Remember, there's no real point source there. There's no atom. I mean, we are assuming everything in vacuum, so there's no other atom, right? The effect of all these spherical wavefronts that come out of each of these points, if you add them all up with the right phase, because remember, phase is important because now we're talking about wavefronts, you will get another envelope to all these little spherical wavefronts. And that envelope is the next wavefront that happens at the next instant of time. Okay? So that's a so-called secondary wavefront. You'll get another sphere, clearly. Right? Because each of these, of course, if you look at the same interval of time, each of these diameters are the same, right? Because they travel the same distance. So what Huygens Principle allows us to do is to predict what the wavefront will be if you know what the wavefront is now. Okay, that's one way to think about it. This is also one form of ray tracing. I'll come to this later on. Okay, one way to think about it, of course, in a spherical wavefront, the rays are all orthogonal to the sphere, right? So, of course, the next one should, if you have a sphere, the next one should also be a sphere. So you can maintain all the rays to be orthogonal again. Okay. So, of course, this is valid for any arbitrary wavefront. So if you have some arbitrary wavefront, let's say. Okay. So most wavefronts are arbitrary, right? So if you look at the light or what your eye sees is some complicated wavefront, right? That's how you form images. And we'll talk about that in a few minutes. But if you want to know what happens next, all you need to do is create a bunch of point sources and create spherical waves from them. And then look at the envelope of all those spherical wavefronts, and you can predict what the next wavefront will be. Okay. Again, of course, in practice, no one does this by hand, right? It's all done by computer. But what's important is you need to understand conceptually what that means. We'll see some ray tracing software examples later on. Okay? So the wavefront after a short propagation distance is the superposition of all the spherical wavelets. That's what each of these points refer to as. Okay, now, like I said before, today we're going to talk mostly about imaging systems. So the first question is, why are imaging systems necessary? So one way to think about it is, say you have an object, light from each point of the object is going in all directions. Okay, so the light from this point of the leaf and the light from this point of the leaf is going in all directions. So a little bit away from the object, all the information is mixed, right? There is no discrimination. So if you don't have an imaging system, you won't see. You won't see anything. In other words, if you do not have your eye, obviously if you just had a retina, you will not make out many objects, right? Or another way to think about it is, if I just take a CCD with no lens or a photographic film with no lens in front of a leaf, I'm not going to form an image of it, right? That's basically what that means. So you need some optics to recreate the properties of the object. Okay? So basically that's what it says. Each point in an object scatters incident illumination into a spherical wavelet according to Huygens Principle. At a short distance from the object, the wavelets from all the points get entangled, mixed together, and object details are relocalized. That's what basically that means. The objective of imaging is to relocalize the object details by assigning. We'll see what that means. That means, in general, is focusing rays from a single object point to a single image point. Yeah, we'll see what that means in a second. But so that's why we need eyes, for instance, to see, right? Okay, so lens is the simplest possible instrument for image formation. What a lens does, it takes a point object and makes a point image. So all the rays that come from one point end up, or as much as possible, obviously they won't be all because you're going to miss some of the rays out here. But most of the rays end up at the same image point. So it's a one-to-one mapping. That's what an imaging system is. Now when we talk about non-imaging optics later on, there will be no one-to-one mapping. Be one-to-many mapping. Or many-to-one, depends on what you're trying to do. Right? Because for instance, if you're doing a solar thermal system, for instance, you're not trying to form an image of the sun. Right? All you're trying to do is transfer energy from the sun to some location. Very different. The imaging systems are a little bit easier to understand. That's why we're starting here. Okay. How does a lens work? Essentially, the curved surface, so your lens is typically made of glass. The curved surface makes the rays bend at angles proportional to the distance from the optical axis according to Snell's law. Thus, the diverging wavefront becomes converging on the output side. That's one way to think about it. So, if you look at the lens, its curvature increases as you go away from the optical axis. So that's the optical axis. Okay. For a ray that goes straight through, it just sees a plane surface, right? It just goes straight. What is the angle of incidence in that case? 0 degrees, because it's always measured from the normal. Of course, when the angle of incidence is 0, from Snell's law, what's the angle of refraction? We're ignoring reflections for now. Let's talk about after the medium. 0, so it goes straight through. That's why if you look at the center of the lens, it's usually flat. Okay? Now as you go further out, the rays have larger and larger angles. If you come at large angles, of course you need to bend more, right? You're trying to bend it down towards the axis. So you need to have a higher curvature, right? So if you have ray that comes in this way and you're trying to send it down this way, so in that situation, if I draw the normal, that's what I'm looking at, right? That's my incident angle, that's my transmitted angle, and let's say that's the point of intersection. That determines the normal to the surface, and if I draw a tangent to the normal, that's the local radius of curvature. Obviously, if I go further out, it has to bend more, right? So you can figure out what the shape of the lens would be. Of course, the ray here, it should be straight. Okay. Now, if you do that mathematically, you can come up with the shape of the lens, and we won't really go into that, but you will see how that is. Okay. Now, there is a technique to analyze optical imaging systems, which is also applicable for non-imaging systems. But again, it's easier to understand for imaging systems. So we'll go through this in some detail. Okay? It's a technique called ray tracing. So to figure out if a ray that passes through optical systems, what happens to it as it passes through. Okay? So to think about it conceptually first, it's very straightforward. You have light rays that come from a point object in all directions. It passes through what can be thought of as free space propagation in air. Then it sees an air-glass interface, so it undergoes refraction. We're ignoring reflections for now. Then you have free space propagation in glass. If you have a thick lens, there's some propagation inside the glass. And then you have another interface, at the glass-air interface. Again, another refraction. And then you have some free space propagation in air, and you'll end up forming an image. Okay? So mathematically, you can describe all of these. Why? Because free space propagation, we know it because free space is a homogeneous medium. Rays will just follow the straight lines. So if you have a ray, you can just draw, right? And we know if we have an interface, we can explain what happens with Snell's law. Right? So that's all we need. So we only need two models. And we can describe the whole system. Okay. So, and we will look at that. But there's an important approximation that we will make in these systems, which is referred to as a paraxial approximation. And this is also true for non-imaging systems. So we will also come back to this later on. But what paraxial approximation essentially means is that we will assume that the rays are always at a small angle to the optical axis. We will ignore rays that come at very large angles. That's essentially what it means. And that has some important implications, that approximation. Okay? Essentially, so what that means is that is epsilon. Only rays close to the optical axis are considered. So epsilon is much smaller than a radian, let's say. And what that means is that you can make very simple approximation to all the trigonometric functions. First order Taylor approximation. So sine epsilon becomes epsilon, tan epsilon becomes epsilon, cos epsilon becomes 1. So simplify Snell's law, right? You can imagine already, and all the geometric considerations. Okay. So typically it's a few tens of degrees. Okay. Now with that in mind, it's relatively straightforward to do. We can apply Snell's law assuming. There's another important consequence of the paraxial approximation is that if you look in detail at what happens to the rays, okay, look at this ray. It is incident on the surface at this point, where this ray is incident on the surface at that point. So it's a little bit shifted. Right? This point is a little bit further down than the other point. Okay. In paraxial approximation, because epsilon is small, we will ignore that shift. That's another important consequence of that approximation. Okay? So essentially, we'll ignore the distance between the actual off-axis ray intersection and the optical axis intersection with the lens. Okay? And clearly, that's only valid for small apertures and thin elements. Okay? So if you have big aperture lenses, it's not quite valid. So I'm going to stop here because we'll have to go through some of the math. So in the interest of time, in the interest of keeping you guys still before you guys go to sleep, I'll save this for next week because you need to understand it a little bit. So we'll stop here, and I want you to. We have a few more minutes, so I want to take the opportunity to. For each team, maybe to give me a 1 second description of where you guys are. Okay, so let's start. We'll start in the very back. Why don't you guys? Faisal, I'll nominate you. I'll pick each.
My group. So we've had our first group discussion, and we've narrowed down our application.
First, remind us what your project is, because I don't remember.
So it's on solar thermal applications.
Yes.
So
okay.
we've decided to proceed with an application on greenhouses using solar and thermal energy. So we've divided our work amongst each other, and we're going to have another meeting next week, following up on background research and things like that.
Okay.
So
and you guys will have something in 2 weeks, right?
Yeah.
Okay.
Oh yes.
Like I said, deadlines are important, so you will need to submit something. Good. I forget your name, so remind me. Dan, okay.
We switched just last week to solar desalination.
Yes.
Not last week, Tuesday.
Yeah.
So we left the past 2 days to kind of like read up on our own. So we're going to meet after this. So we haven't split it up or narrowed it down yet.
Okay.
Because of that change.
Okay. But I would plan on doing it soon.
So we're
so
meeting after class to split up or discuss what we've read and then split it up and then. Yeah.
Okay, good. The other strategy, of course, is you can do a review, right? So you can use this opportunity to do a literature review on seeing what are things out there, and then narrow it for the next report. That's also okay.
Okay.
So it depends what you want to do. So make sure you reference well what you write. I'm just going to pick you guys in the background. What about you, Nelson?
So we're the hybrid systems.
Yes, okay.
Team. We decided to kind of think, because there's a vast amount of possibilities with those.
Yes, exactly. Yeah.
We decided to kind of research a bunch of different types individually, come together next week, and kind of pick a topic that we think would be most interesting or best for us. And then
okay. Yeah. Now, if you feel like if you're getting too diffuse, make sure you come and talk to me. You're on the team, I remember. So make sure talk to me and let's discuss. But again, like I said, you can take the opportunity to do a survey and see what's out there, because there are solutions out there people already built or proposed and so on. And take a look at it.
Good.
That's good. Xiaowen?
We are photovoltaics group, and this Monday we have a meeting to discuss our everybody task for everybody. We decide to give a review of history of PV and especially concentrated on CPV, and there are various types and advantages and disadvantages between them, and next week we'll give a draft for the paper.
Okay, that's good. Yeah, in your case, when I said PV, I would focus certainly on CPV, because PV is very broad, right? You can talk about lots of things, but focus more on the optics, I'd say.
Okay.
I mean, it's more than enough material for CPV as well.
Yeah.
Again, at some point you should narrow it down. Look, for the first report, you can do a broad literature search, but for the next one on, I would narrow it to some particular thing that you're interested in focusing on, right?
Yeah.
So you'll have to pick something.
Oh.
I'm in the hybrid system.
Okay, so
So
heroes.
the same.
Okay, good. What about you?
So we are the.
Remind me your name.
My name is Xiao
Xiaoyu. Okay.
Yeah, and we are the solar refrigeration.
Oh,
and,
good. Yeah,
slash
yeah.
air conditioning group, and we decided for the first assignment there are 3 types of refrigeration.
Mhm.
So I think since there are 3 members in our team, and we are gonna just split.
Okay.
Each of us gonna do a special, specific type
Okay.
of the, yeah.
Okay, good.
And then, and in the end, we just combine these 3
Okay.
report together.
Yeah. Now, one thing to remember about the reports, make sure, again, you only get 3 pages, and make
Yeah.
sure you. I'm going to grade them, and I'll give them to you with some feedback, so you see, because writing is also an important part to learn. So make sure it kind of flows. Like 3 people write 3
Yeah.
different things. Make sure it kind of makes
We're
sense
gonna
together.
Meet
Yeah.
together in the end.
Okay,
Yeah.
good. Was there another project that I missed? Did we get all the projects? What were you on?
In the desalinization as well.
Okay, good. Okay, I think we're all set. I'm going to stop here. So.